Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is chapter 4.7, which is on inverse trigonometry. Right, so inverse trig. So first, let's recall what y equals sine of x looks like. Right, now y equals sine of x is the following function. It is a wave that starts at 0, goes up and down in both directions forever and ever, right? Now, the thing about this function is that it fails something called the horizontal line test, all right? So because it fails the horizontal line test, no true inverse exists. Why? Well, the thing is that to have an inverse function, we need to make sure that we're working with a one-to-one function. And this is not a one-to-one function because it fails the horizontal line test, right? So what we need to do is we need to restrict the domain so that it is a one-to-one function. And the way we're going to do that is, well, we're going to look at this piece right here. Actually, nope, that's not it. This piece. There we go. That piece right there happens to be one-to-one because in there it would actually pass horizontal line test. And in here we're going to go from negative pi over 2 to positive pi over 2. So that is the domain we're going to be looking at. So if we look at y equals sine of x restricted, and this is going to be restricted from negative pi over 2 to positive pi over 2, then we get the following. All right, let's do that better. And the restricted function would just be something like this. It would go from negative pi over 2 to positive pi over 2. The range would still be from negative 1 to positive 1. And it would look something like this. All right, so that's the restricted sine function. In order to look at the inverse of this, so I'm going to look at y equals sine inverse. Well, this is going to do the exact opposite of this. And what do we mean by that? Well, we know that when we're talking about a function and its inverse, the domain and the range switches. So in here, the domain is going to be from negative 1 to 1, right? Because in here, the range is from negative 1 to 1 for regular sine. Similarly, for sine inverse, the range is going to be from negative pi over 2 to positive pi over 2. And sine inverse will look as follows. So let's put this on the graph. So our domain is from negative 1 to 1. And our range is from negative pi over 2 to positive pi over 2. And our function ends up looking like this. All right, something like that. Now, notice here that visually speaking, these graphs are, well, if I do them better, you will see that these graphs are actually mirror image about the y equals x-axis. All right. Maybe if I drew this one a little bit better. Let's see. So something like that. And our line, nope, this is not any better. Let's stay within that line then. The point is that these two would be mirror images about the line y equals x. All right. Now, as we already said, the domain becomes the range, and the range, so the domain becomes the range, and the range becomes the domain. Now, so maybe we should define something here. In general, we can say that the inverse of sine, or maybe already the inverse of sine of x, is sine inverse of x, or arcsine of x. All right. Either way, those two are saying the same exact thing: sine inverse or arcsine. And when I have something like y is equal to arcsine of x, this is equivalent to saying that sine of y equals x. Similarly, if I have y equals sine inverse of x, this is equivalent to saying that sine of y equals x. So arcsine and sine inverse are saying the same exact thing. And in here, where x is between -1 and 1, right, for the input here, and y is between -π/2 to +π/2. So again, that's the domain and the range. All right. So right there here, domain and range. Now, that's for sine. Let's repeat the same exact stuff, but for cosine. So first, let's look at y equals cosine of x. And y equals cosine of x looks as follows, right? It is a wave that starts at 1, and it repeats forever and ever, right? And notice here that we have the same issue that we had with sine, meaning that it fails the horizontal line test, right? Maybe I'll do it a little bit lower. There we go. It fails the horizontal line test. So, which implies no true inverse exists. However, we already know how to get around that. All we need to do is restrict the domain. And in this case, we're going to restrict it this way. We're going to say this piece right here is what we're going to be looking at. We're going to go from 0 all the way up to pi. All right. So if we look at y equals cosine of x restricted from 0 to pi, so that's the domain I'm going to be looking at. Notice that in that region, it spans the entire range from -1 to 1. All right. Now, what does the restricted cosine function look like? Well, let's look at it. If I've got the domain going from 0 to pi, let's write that better. There we go. If I've got the domain going from 0 to pi, it does this. Let's say that this right here is 1, and this right here is -1. It starts at 1, crosses at pi/2, gets all the way down to -1 by the time we get to pi. All right, so that's essentially what that looks like. That's the restricted cosine function. If I look at y equals cosine inverse of x, all right, in here the domain is going to be from -1 to 1, and the range is going to be from 0 to pi. And the way this function looks is as follows. Perhaps I'll draw this a little bit better this way. All right. So our domain is from -1 to 1. Our range is from 0 to pi. Let's say this up here is pi, and it does the following. At 1, it hits it over here. At pi over 2, it hits it somewhere around there. And at -1, it hits it all the way up here. And it looks something like this. All right. So that would be the graph of cosine inverse of x. And just like before, if I write y equals cosine of x, this is equivalent to saying, oh, hold on, that's not what I meant to write. If I write y equals cosine inverse of x, this is equivalent to saying that cosine of y equals x. Similarly, I can say arc cosine instead of cosine inverse, and it will give me the same exact thing. Either way, the domain is from -1 to 1, and the range is from 0 to pi. So let's look at how we can evaluate these functions then. And the best way to do so is by using the unit circle. So let's go ahead and pull up the unit circle. And there it is. Now, the thing about this unit circle, as far as this is concerned, and first I'll remind you of something before I say it. If you recall, when we said that the domain for y equals sine inverse of x, actually let's look at the range. The range was from -pi over 2 to +pi over 2, and for y equals cosine inverse of x, the range was from 0 to pi. Well, what does that tell us in regards to this unit circle is that sine inverse would exist on the right half of the unit circle, whereas cosine inverse would exist on the top half of the unit circle. All right, and why would that be? Well, because, well, if you look at this unit circle, we know that down here is 3 pi over 2, but it is also coterminal to -pi over 2, right? So if I look at these angles right here as negative angles, 11 pi over 6 would be -pi over 6, 7 pi over 4 would be -pi over 4, 5 pi over 3 would be -pi over 3, and 3 pi over 2 would be -pi over 2, meaning that all of those would be, or this entire half on this side, would be in the range of sine inverse. All right, this entire half. And similarly, for cosine, well, because the range of cosine inverse is from 0 to pi, it's going to be entirely on the top half, from 0 all the way up to pi. So when I ask the question of something like, let's rewrite this. When I ask the question, what is sine inverse of 1, for example? All right, well, this one's easy. There's only one spot on the unit circle that has that, right? If I look at the y values of the unit circle, this is the only spot where I have sine being equal to 1. So sine inverse of 1 is simply pi over 2. Similarly, if I said cosine inverse of 1, well, I would look at the x values to see where cosine would be equal to 1. And that happens at this part right here, which happens to be at 0. 0 is in the range of cosine inverse, so we're good. There we go. But let's look at some other ones. If I said something like sine inverse of radical 2 over 2, well, we would say, well, in here, where is the y value equal to radical 2 over 2? And we say, well, there's two spots. One right here, radical 2 over 2 at 3 pi over 4. And the other one right here, radical 2 over 2 at pi over 4. However, we know that the range for sine inverse is just on the right-hand side of the unit circle. So this value over here at 3 pi over 4 would not work. And the only possible answer is pi over 4. Similarly, if I said something like cosine inverse of radical 3 over 2, we would say, well, let's look at the x values for cosine and see which ones are actually radical 3 over 2. And we see that it happens at two spots. It happens here, here, radical 3 over 2 at pi over 6, but also here, radical 3 over 2 at 11 pi over 6. But we know that for cosine inverse, the range exists in the top half of the unit circle, so the only one that could possibly make sense is pi over 6. All right. Next one. So, but if I said sine inverse of negative radical, actually let's do negative 1/2. Sine inverse of negative 1/2. Well, we will look at where sine is equal to negative 1/2 on the unit circle, and we have that two spaces here. Here at 7 pi over 6, that's where sine is equal to negative 1/2, but also here at 11 pi over 6, y is equal to negative 1/2. So we know that for sine inverse, the range must be on the right side of the unit circle. So this one over here at 7 pi over 6, we don't care about. We care about this one, 11 pi over 6. But the thing about 11 pi over 6 is this is not in the range of sine inverse, right? The range of sine inverse went from negative pi over 2 to positive pi over 2. So our output cannot be outside of that range. So what we do is, well, we look at 11 pi over 6 and find a coterminal angle that is within negative pi over 2 to pi over 2. And the way we're going to do that is we're going to subtract 2 pi. Notice that 2 pi is the same thing as saying 12 pi over 6. So this would give me simply negative pi over 6. So we end up with negative pi over 6 for sine inverse there. All right. For cosine inverse, let's say for cosine inverse, I ask for cosine inverse of negative radical 2 over 2. All right. Well, we will look at cosine inverse. We will look at all the cosine values and say, well, where is there an x value of negative radical 2 over 2? Well, there's one, and here's the other one. But we know that for cosine inverse, our range must be between 0 and pi, so in the top half of the unit circle, meaning that the only possible answer here is at this spot, being at 3 pi over 4. Right? I'll do one more. Let's say that I have sine inverse of negative radical 3 over 2. Sine inverse of negative radical 3 over 2, well, we look at all the sine values. So when we have negative radical 3 over 2, we have them at two spots. Here at 4 pi over 3, as well as here at 5 pi over 3. All right, that's where we got the sine value being negative radical 3 over 2. But we know that for the sine inverse, our range must be on the right hand of the unit circle. So this value at 4 pi over 3, completely irrelevant. So our only possible spot would be here at 5 pi over 3. But the problem with 5 pi over 3 is that it is outside of the range of sine inverse. Remember, we need to be between negative pi over 2 and positive pi over 2. So we would take a look at a coterminal angle, and this would give me, well, in here, 2 pi is the same thing as saying 6 pi over 3. So 5 pi over 3 minus 6 pi over 3 is negative pi over 3, and that would be our solution there. So we need to make sure that for the sine values, we are between the range of negative pi over 2 to positive pi over 2. So all of these values down here in the fourth quadrant, as well as down here the y-axis, we need to look at a coterminal angle within the range. All right, so that is how you read the unit circle for sine inverse and cosine inverse. Now, let's talk about tan inverse. And here we go. So before we look at tan inverse, let's first recall what y equals tan of x looks like. All right, and tangent looks as follows. It's got a whole bunch of vertical asymptotes, and it just keeps repeating itself, right? So the graph itself looks like this, right? And it repeats forever and ever in both directions. But just like before, this happens to fail the horizontal line test. So because it fails the horizontal line test, this tells us no true inverse exists. But we already know how to work around that. And the way we do that is by restricting the domain, and we're going to restrict it just in this region right here. All right. Because that is enough to do the entire range of the function, right? And still pass the horizontal line test, still make it a one-to-one function. So we're going to restrict it to that. Now let's look at just what tan of x restricted looks like. So if I look at y equals tan of x, and we're going to restrict it from negative pi over 2 to positive pi over 2, that's our domain. Our range is all real numbers. It goes from negative infinity to positive infinity. And tan restricted looks like this. We've got our vertical asymptotes at negative pi over 2 and positive pi over 2. And it is just this piece, right? Now, that's y equals tan. So now let's look at what tan inverse looks like. So y equals tan inverse of x. Now we know that the domain and the range are supposed to switch. So the domain would be from negative infinity to positive infinity, and the range would be from negative pi over 2 to positive pi over 2. And I should not be including those values, so let's fix that. I can't include them because they're asymptotes, right? So it has to be open parentheses there. Now, what would the graph of tan inverse look like? Well, it goes as follows. Let's try that again. All right. So it would have now this vertical asymptotes of negative pi over 2 and positive pi over 2. They will become horizontal asymptotes at those exact spots for at pi over 2 and then negative pi over 2. So there is our horizontal asymptotes. Now the graph itself looks as follows. Oh, that's awful. Let's try that again. Less awful, but it gets the point across. Now, in here, well, so that's our range, right? From negative pi over 2 to pi over 2, and that's what tan inverse looks like. Now, just like before, we can talk about whenever we say something like y equals tan inverse of x, we're saying, well, this is equivalent to saying x equals tan of y. Similarly, if I have arctan of x, right, it's the same thing as saying tan inverse, so this is equivalent to saying that x is equal to or tan of y. And in here, this is for the domain going from negative infinity to positive infinity, and the range going from negative pi over 2 to positive pi over 2. So notice here that this is the range is from negative pi over 2 to pi over 2, just like it was for sine inverse. So this tells us that we're going to be looking at the right half of the unit circle when we go to evaluate tan inverse. So let's look at the unit circle again. There it is. So again, we're going to be working on this side of the unit circle. All right. So let's do that. Let's do a couple of examples. So I believe I'm example H. So if I said something like, what is tan inverse of 1? So for tan inverse of 1, well, recall that this is saying, what is the angle such that, so let me rewrite that. at what angle is tan theta equal to 1? That's essentially what this question is asking. Now this right here can be rewritten to say, well, since tan theta is sine over cosine, so this tells us that sine theta over cosine theta is equal to 1. This is equivalent to saying that sine theta is equal to cosine theta. So this question is really asking, where is sine equal to cosine theta on the unit circle? And well, it happens at two spots. It happens up here at pi over 4, they're equal to each other, sine and cosine. But it also happens over here at 5 pi over 4, they're equal to each other. And the thing about this is that 5 pi over 4 is not in the range of tan inverse, so the only value that we would care about is pi over 4. So tan inverse of 1 is simply pi over 4. If I said, what is tan inverse of negative 1? All right, well, by similar reasoning, I would get that this is really asking, where is sine theta equal to negative cosine theta? So where is sine equal to the negative version of cosine? And well, it happens at two spots as well. First here at 3 pi over 4, right? Sine and cosine are negatives of each other. But also over here at 7 pi over 4, sine and cosine are negatives of each other. But we know that for tan inverse, the range is on the right hand side of the unit circle, so the only possible spot is 7 pi over 4. However, 7 pi over 4 is not in the unit circle, so we need to, it's not in the range of tan inverse, so we need to find a coterminal angle that is in the range. And in here, notice that 2 pi is the same as saying 8 pi over 4, so we end up with negative pi over 4. So tan inverse of negative 1 is negative pi over 4. Let's look at another one. Let's say that I ask for what is tan inverse of, let's do radical 3. All right? What is tan inverse of radical 3? Now in here, this is really saying, what is theta, or at what angle, what is theta, such that tan theta is equal to radical 3. All right, so here's where things get tricky for tan inverse and tangent. What we need to really do here for a value like this, we need to multiply this by 1. And the one that we're going to multiply it by is 1/2 over 1/2. Essentially giving me that this becomes just radical 3 over 2 over 1/2. Now, why would I want that? Well, the reason is that we can think of this as sine theta over cosine theta is equal to radical 3 over 2 over 1/2. So we're really looking at where sine theta is radical 3 and where cosine theta is equal to 1/2. Or where they're both negative, right? That would also yield the same exact thing over here. But if you look at the unit circle, well, let's see. Sine being equal to radical 3 over 2 and cosine equal to 1/2, that happens here at pi over 3. All right, that's a pretty good candidate. And the other possible candidate would be over here at 4 pi over 3, because that would give us sine being negative radical 3 and cosine being negative 1/2. So those negatives will cancel out and give us a positive value. But the problem with 4 pi over 3 is that it is outside of the range of tan inverse. Tan inverse is on the right hand of the unit circle, so the only possible answer here is pi over 3. All right. Let's look at another one kind of like this. If I said, what is tan inverse of, let's do negative 1 over radical 3. All right. If I look at tan inverse of negative 1 over radical 3, well, using the similar way that I did before, I can say this is really saying that tan theta is equal to negative 1 over radical 3, and we're trying to figure out what that theta would be. And I'm going to apply the same exact trick of multiplying by 1, and that 1 is going to be the same exact as before, 1/2 over 1/2. And what this gives me is I end up with a negative of 1/2 over radical 3 over 2. And I care about this because tangent is the same thing as saying sine theta over cosine theta. And I've got this being equal to the negative of 1/2 over radical 3 over 2. Now recall that this is really the same thing as saying the negative of 1/2 over radical 3 over 2, or 1/2 over the negative of radical 3 over 2. So essentially we're either looking for sine to be negative or for cosine to be negative, but not both. So that means we're, as far as the unit circle is concerned, we're either working up here or down here. And for sine to be equal to 1/2, if we're up here, it would be right here. There's sine being 1/2 and cosine being equal to negative radical 3 over 2. But that would be at 5 pi over 6, and 5 pi over 6 is not within the range of tan inverse. The only possible value would be down here then, at 11 pi over 6, because the cosine value is radical 3 over 2, and the sine value is negative 1/2, just like what we have here. All right. However, 11 pi over 6 is not in the range of tan inverse. So what we do is we would look at 11 pi over 6 and find a coterminal angle by subtracting 2 pi. And here 2 pi is the same thing as saying 12 pi over 6. So I get just simply negative pi over 6. And that would be my solution here. Tan inverse of negative 1 over radical 3 is negative pi over 6. All right. Similarly, I'll do one more. Let's do just tan inverse of negative radical 3. All right. So in here, I'm going to say, well, this is really saying that tan theta is equal to negative radical 3, which is equivalent to saying that sine theta over cosine theta is negative radical 3. And I'm going to apply the same exact trick as before, multiply by 1. All right, where that 1 is 1/2 over 1/2. And this gives me negative radical 3 over 2 over 1/2. Now, anytime you're really evaluating tan inverse, it's really the sine value that's possibly negative. All right, and the reason for that is because we're working on the right half of the unit circle for tan inverse, and on the right half of the unit circle for tan in general, cosine is positive, right? All the x values are positive, so you really should be looking at making the sine version or the sine part negative. So we're looking at, well, where is sine equal to negative radical 3 over 2 and cosine equal to positive 1/2? Well, there it is. Sine is negative radical 3 over 2 right there. Cosine is equal to 1/2, so it would be at 5 pi over 3. But we know that 5 pi over 3 is not in the range of tan inverse, so we're going to find a coterminal angle by subtracting 2 pi. In this case, 2 pi is the same thing as saying 6 pi over 3, and 5 pi over 3 minus 6 pi over 3 is just simply negative pi over 3. So that is our solution here, negative pi over 3. All right. All right, so that's sine, cosine, and tan inverse. I'm not going to be focusing on arc secant, arc cosecant, and arc cotangent. All right. Just for sine, so I'm only going to be looking at arc sine, arc cosine, and arc tangent. But now, let's move on from evaluating these. Let's talk about compositions with inverse trig functions. All right. So compositions with inverse trig functions. All right. So first, recall something. Recall that if I compose f inverse with f of x, that just gives me x. Similarly, if I compose f with f inverse, that also just gives me x, excuse me. All right. So we're going to be using that to our advantage. Now, let's look at the properties for this. So the properties. So if x is between -1 and 1, and y is between -π/2 to +π/2, then we get that sine of sine inverse of x is equal to x, and sine inverse of sine of y is equal to y. Notice here that it matters on what the domain is. All right, so what I'm talking about here is that if I have the domain here being between -1 and 1, then I have sine inverse on the inside. But if I've got the domain being between -π/2 to π/2, then I've got sine on the inside. All right. Similarly, if x is between -1 and 1, and y is between 0 and pi, then we could say that cosine of cosine inverse is equal to x, and cosine inverse of cosine of y is just equal to y, right? So essentially, as long as you're working with the proper domains, these would cancel each other out. If x is between, actually if x is any real number, so if x is a real number and y is between -π/2 and +π/2, not including them, so strictly between -π/2 and +π/2, then we would get that tangent of tan inverse is equal to x, and tan inverse of tan of y is equal to just y. So again, as long as you're working within the proper domains, they would cancel each other out. All right, so notice that I said that as long as you're working within the proper domains. All right, I said that about all of these. In here, well, what does that mean? Well, so perhaps I'll write a note here. Note: sine inverse of sine of 3π/2 is not 3π/2. All right, sine inverse of sine of 3π/2 is not 3π/2. And why would that be? Well, the reason for that is because, well, 3π/2 is not within the domain for this part over here, right? If I have this stuff happening, sine inverse of sine, the only way they cancel out is if y value is between -π/2 and +π/2, and here our y value being 3π/2 is not within that. So what we need to actually do here is, well, we need to do this one step at a time. Sine inverse of sine of 3π/2. Well, sine of 3π/2, if you recall from the unit circle, and perhaps I'll put it up real quick, sine inverse of 3π, sine of 3π/2 is -1. So we're going to say that in here, sine of 3π/2 is -1, which then tells us sine inverse of -1, well, we're working down here, sine inverse of -1, here at 3π/2, well, 3π/2 is not in the range of sine inverse, so we would say that that's just simply -π/2, right? Because we want to read that as a negative angle. So even though these are two coterminal angles, they're not the same exact value, right? 3π/2 and -π/2, they're coterminal angles, but they're not the same value. So you have to be careful about that, all right? You have to be careful about when you're working with sine, well, with trig inverse functions, that they are actually what they're supposed to be. So, all right. So let's look at a couple of examples. and I believe I'm at example M. So if I have something like tan inverse of negative 14, well, what would that be? Well, let's see. For tan inverse in here, that's the setup I have, and it just has to be the x the real number, and then it's just the inside. They just cancel each other out. So for tan and tan inverse being composed this way, pretty simple, just negative 14. We don't need the unit circle. Let's take that away. All right. And let's say that I had something like cosine inverse of cosine of 7 pi over 4. Well, in here, I'm going to tell you already that this is not 7 pi over 4. All right? They don't just cancel out this way. So let's see what actually happens. So we have cosine inverse of cosine of 7 pi over 4. Now what we're going to look at is, well, from the unit circle, what is cosine of 7 pi over 4? You should have that already memorized. Cosine of 7 pi over 4 is negative radical 2 over 2. That's not true. It's positive radical 2 over 2. Sorry. So it's at positive radical 2 over 2. And at that point we say, well, what's cosine inverse of positive radical 2 over 2? It is actually pi over 4. So I'll pull up the unit circle again real quick so you can see what I did. So we said cosine of 7 pi over 4. Well, I go to 7 pi over 4, and I go to cosine value, radical 2 over 2. And then I said, well, what is cosine inverse of radical 2 over 2? Well, I can't be working with this down here because it's outside of the range of cosine inverse. Cosine inverse exists on the top half of the unit circle. So in the top half of the unit circle, where is cosine equal to radical 2 over 2? Right there. So the answer is pi over 4. All right. Oh, let's say that I have sine of sine inverse of pi. All right. Sine of sine inverse of pi. Now in here, I'm going to tell you right away what the answer is. It's undefined. Now, why would that be? Well, perhaps I'll copy this real quick so that I can reference it as I'm talking about it. And here we go. So if you recall this, I have sine of sine inverse. So I'm looking at this version down here, sine of sine inverse, right? And in sine of sine inverse, we have that the x value must be between negative 1 and 1. So in here, this value right here is supposed to be between negative 1 and 1. So pi, however, is not between negative 1 and 1. Pi is above that, right? So in here, I can't even work with that. And in fact, normally we don't plug in angles into the inverse. So that should also have been a hint that this would not possibly work. All right. So again, the reason why this is undefined is since pi is not between negative 1 and 1. All right. Which is what we need for this. All right. Now, that's all exciting, but let's move on from this. Let's talk about evaluating these compositions using triangles. Evaluating compositions using triangles. All right. So, and what letter am I at? Oh, so P. So let's say that I have tangent of cosine inverse of 2/3, right? This is fine, cosine inverse of 2/3, right? Because the domain for cosine inverse is between -1 and 1, and 2/3 is between -1 and 1. So what do we actually have to do here? Well, since we're working with cosine inverse, that means that the triangle, actually let's do this. This piece right here is some sort of angle. So what I'm going to look at is that this angle is equal to cosine inverse of 2/3, which implies that cosine theta is equal to 2/3. All right. Now, at that point, we need to come up with a triangle for that. And there are two possible triangles that would work here. We could either write this triangle or this triangle, but only one of them makes sense. Recall that cosine inverse exists only on the top half of the unit circle, so cosine inverse must be on the top half. And we have a positive value there, 2/3, meaning that we had to be on the first quadrant. If we had cosine inverse with a negative value, we'd be in the second quadrant. So we're in the first quadrant. All right, here's our theta. And we say that, well, cosine is 2/3, cosine is adjacent over hypotenuse, giving me that this side over here, well, from the Pythagorean theorem, we end up with the square root of 5, right? A squared plus b squared equals c squared. That's how I get this. So I end up with radical 5 on that side. And now I'm looking for tangent of this angle, tangent of cosine inverse of 2/3. And tangent is opposite over adjacent, so we have radical 5 over 2. All right, so tangent of cosine inverse of 2/3 is radical 5/2, or radical 5 over 2. Let's do another one. If I said something like cosine of sine inverse of -3/5, all right? Well, the first thing I'm going to say is that this inside here, that's the input for cosine, that should be an angle. So I have that theta is equal to sine inverse of -3/5, which really tells me that sine theta is equal to -3/5. Now, as far as what this triangle would look like, well, since we're working with sine inverse, our triangle must exist on the right half side, right? But not just that, we're working with a negative value here, so that tells us that our triangle would have to be on the fourth quadrant, all right? And again, sine inverse must be on the right hand side, negative value, bottom part. Now, we've got the sine is equal to -3/5, so from SOHCAHTOA, the opposite being -3, the hypotenuse being 5. At that point, using the Pythagorean theorem, or recognizing that this is a Pythagorean triple, we would say that the adjacent side is 4. At that point, well, cosine of that, well, cosine theta now, well, from SOHCAHTOA, cosine is adjacent over hypotenuse, so it's just 4/5. All right. Let's do another one. So that was Q. R. Let's say that I have sine of tan inverse of -12/5. All right. And again, we start by saying, well, this inside here must be some sort of theta. So theta is equal to tan inverse of -12/5. So that tan theta is equal to -12/5. And then we realize, well, what would this look like on the graph? Well, there's two possibilities here, because tan inverse, just like sine inverse, exists only on the right half side of this. And since you're working with tangent here, or tan inverse being negative, the inside being negative, that means that our triangle must be down here. Let's draw that better. There we go. Now, tan being negative 12 over 5, well, from SOHCAHTOA, tangent is opposite over adjacent. So the possibilities here are that I either have negative 12 over 5 or 12 over negative 5. But because we're working in this quadrant over here, we're going to say that the opposite is negative 12. The adjacent is a positive 5. All right, so essentially we're saying this one didn't work. Now, this right here, you might recognize this to be another Pythagorean triple. This is a 5, 12, 13 triangle. All right. If you didn't recognize that, you can do the Pythagorean theorem to figure out what the hypotenuse would be. But now that we have this, we can figure out what sine of that angle is supposed to be. So I would say that sine theta, SOHCAHTOA, is opposite over hypotenuse, so negative 12 over 13. All right. Now let's extend this idea. Let's extend this idea to have algebraic expressions. All right. So write an algebraic expression that is equivalent to the given expression. All right. So what letter was I at? R? Yeah. So S. Let's say that I have sine of our cosine or cosine inverse of 3x, and I'm saying here that x is between 0 and 1/3. All right. So in general, when we have this, well, just like before, we would say that this inside here is our theta. So since theta would be equal to cosine inverse, I'm just going to write this cosine inverse of 3x, that tells us that cosine theta is equal to 3x. So from SOHCAHTOA, I can just write this generic triangle and say that, well, from SOHCAHTOA, the adjacent is 3x, the hypotenuse is 1, right? This is 3x over 1. And what would this side over here be? Well, from the Pythagorean theorem, that would be, and maybe I'll write it this way, we have a squared plus b squared equals c squared, so that a, well, let's solve for b. So that b is equal to the square root of c squared minus a squared. All right, which is how I get here the square root of 1 minus 9x squared. All right, this is 1 squared minus 3x quantity squared, so that's 9x squared. So now that I have that, I can figure out what sine is, right? So I can say now that sine of that angle from SOHCAHTOA is opposite of our hypotenuse, so it's just a square root of 1 minus 9x squared. All right. Let's do another one. Let's say that I had, so that's S, T. Let's say that I asked for cotangent of sine inverse of 5x. And in here, I'm going to force x to be between 0 and 1/5, just for easy values. As far as what this extra stuff is concerned, it essentially forces the angle to stay positive. All right, so that we're working in a nice quadrant. All right. Similarly here, this forces this angle to stay, I should say, non-negative. But yeah. Anywho, now let's do the same exact thing. This inside was our theta, so theta is equal to sine inverse of 5x. So that sine theta is equal to just simply 5x. And what we're going to do with this is, well, 5x is the same thing as saying 5x over 1, right? So what we're going to say is that if I draw this triangle, sine is opposite over hypotenuse. So here's 5x, here's 1. And from the Pythagorean theorem, that would tell me that this side over here is 1 minus 25x squared, right? 1 minus 25x squared. And I'm looking for cotangent of that angle. So cotangent of theta, cotangent is a reciprocal of tangent. Tangent was opposite over adjacent. So cotangent would be adjacent over the opposite, which is how I get the square root of 1 minus 25x squared. All of that over 5x. Adjacent over the opposite, right? All right, let's do another one. So that's T. U. Let's say that I've got something like cosecant of tan inverse of, let's do x over 3. All right, cosecant of tan inverse of x over 3. Now in here, we don't need to worry about the inside too much because, well, tan inverse, the domain is all real numbers, so anything here will be fine. So let's go ahead and take a look at how to work with this. Like before, we're going to say that the inside is theta, so theta is equal to tan inverse of x over 3. So that tan theta is equal to just simply x over 3. So if I draw the triangle now, from SOHCAHTOA, we know that tangent is opposite over adjacent, so I end up with the opposite over the adjacent, meaning that the hypotenuse here is going to be, by the Pythagorean theorem, x squared plus, not plus 3, x squared plus 9, right? Because remember, it's a squared plus b squared equals c squared. So here, right here is our theta. And now I can see, well, what would cosecant be? Cosecant of that angle, cosecant is a reciprocal of sine. Sine is opposite over hypotenuse. So I get the hypotenuse over the opposite. All right. Let's do another one. That was U. V. Let's say that I have cosine of tan inverse of 7 over 4x. Well, in here, like before, this is our theta. So what we have here is that tan theta is equal to 7 over 4x. And if I go ahead and draw the triangle now, and hold on, I skipped the method. Theta is equal to tan inverse of 7 over 4x. So that tan theta is equal to 7 over 4x. There we go. And now if I take a look at the triangle implied, well, tangent is opposite over adjacent. So I end up with opposite, the adjacent, giving me that the hypotenuse is going to be 16x squared plus 49. And again, that's from the Pythagorean theorem. At that point, we would say, well, what would cosine of that angle be? So cosine theta from SOHCAHTOA is adjacent over hypotenuse. So I end up with our adjacent side, 4x, over the hypotenuse, 16x squared plus 49. All right. And that would be our final answer. All right. That concludes 4.7.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.